Hi everybody. In this video I'm going to give you an introduction to supervised classification and a few of the most common classification algorithms. So we'll start out talking about training data, then we'll look at the decision tree algorithm, minimum distance to the mean, maximum likelihood, and fuzzy classification. So as a reminder, in classification our goal is to go from some kind of image where each pixel is essentially a number and assign each of those pixels into a class where we might be able to have a map. And we can think of two types of classes. One are user classes. These are defined by the user and are usually functional surface types. In this case, we're going to talk about Yellowstone National Park, so we might talk about burned areas versus unburned, or water versus rock. Those are examples of user classes. And I'll also say there's two types of classification. Supervised, that we're about to talk about today, where we're going to divide the image into these user classes, okay? And in the next video, we'll talk about unsupervised classification, where we'd be dividing the image into spectral classes. So tune in for that if you're interested. Supervised classification has three stages. The first is the training stage, where we're going to define our user classes and then collect spectra from each class so that we can train the computer what each class looks like, basically what its spectral signature is. Next is the classification stage, when we'll actually run one of the algorithms, which will consider each pixel individually and classify it into one of our predefined user classes. And then we've got the output stage, where we'll usually filter the results to create some kind of map or statistics. And it's important to know classification is never 100% successful. So actually the post-processing and the output stage can be incredibly important to clean up your classified map. So what is training data? It can come from different places, and really it can be anything, any of your inputs. In this example, we're going to show you how to use user-extracted image data. Basically, we're going to go to the image, we're going to go to surfaces, areas of the image where we know it's one of the user classes, and draw a polygon around it. So here's what that might look like, right? If we wanted to have water as one of our end members, we would circle a polygon around water, and the software would extract all the pixels from in that polygon and aggregate their mean spectral signature. Okay, and then we might do the same for different types of fields. So for each user class we have, we're going to draw a polygon around it, and it can be multiple polygons, and then aggregate those pixels and look at the mean spectral signature of those pixels within the polygon. And that will be our training data. So in this video, we're going to look at Yellowstone National Park. So here's our training polygons. We got one for water, meadow, burned forest, unburned forest, and rock down here. So we have 5 user classes. And our first algorithm is the decision tree algorithm. So the way this works is you take your first pixel, or any of your pixels, and you ask it a series of questions. So in this example, the first thing we'd ask is, what is your reflectance in the near infrared? Okay? If it's reflecting less than 10% in the near infrared, we can say right away that pixel is water. If it's greater than 10%, well, it could still be anything. So we go down this branch of the tree. Next, we ask, what's your reflectance in the green wavelength? Okay? If it's less than 30% in the green wavelength, then we're going to suspect that it is not forest or crops, right? It's not green enough to be forest or crops. That puts us down this branch. And then you can even use like a decision-making table here, where we'll consider the red band and a shortwave infrared band. So if it's greater than 30% reflectance in the red, but less than 40% in the shortwave, it is very likely to be urban, okay? And so on with these other categories. And likewise, if it was reflecting greater than 30% in the green, we'd go down this. And then, now this is interesting, here in this example, we're actually going to consider elevation. We're going to bring in something that's not spectral data, some other type of data. In this case, it's going to be elevation from a digital elevation model, a DEM. So if it was a green pixel, if it's less than 800 meters, we're going to categorize it into irrigated crops, right? Farm fields are in the valleys at low elevation. If it's greater than 800 meters, up on a mountainside, we're going to call it a deciduous tree. So this is an example, and you can customize each of these decisions. You get to have complete control over which bands you're looking at and what your cutoff thresholds are. And you can actually, lots of ways you can iterate these decision trees until you can kind of customize them to be the most accurate as possible. So our next algorithm is the minimum distance to the mean. And in order to think about this algorithm, you need to think about each training data set. So each training data for each user class has multiple bands, right? You drew a polygon and you took the mean of the pixels, not just for one band, but for like 5 or 6 bands. So we can actually plot these bands against each other, okay? So for water is low reflectance in band 4 and low in band 3. So it sits all the way over here. Forest, on the other hand, is high in band 4, but is low in band 3. So it occupies a different kind of space in this bivariate plot. So now to classify, let's imagine we have 2 unknown pixels. Let's look at pixel 1 first. We don't know what this pixel is. We don't know what group it belongs to. But we do know its digital number for band 3 and for band 4. We plot it right there, and we see that it's closest to corn. And by closest, I mean the distance between its position and the mean of the corn values is the shortest. So that's why it's called minimum distance to the mean, because you're going to the mean of these groups. All right, let's look at another one. Here's another point number 2. Now this one's a little trickier, right? And this illustrates the weakness of this method. It clearly falls within the urban group, right? But because it's on the outlying edge of the urban group, it actually is closest to sand, S. So this would actually be classified as sand, and really that would probably be a misclassification. And that underscores the weakness of this technique, which is that it's insensitive to the variance in the data, right? Because you're just using a simple mean, it's not sensitive to the spread in the data. It had no way to know that urban was spread out so much. Before we move on here, I'll just say minimum distance to mean, in this example, we've used 2 dimensions, okay? Band 4 versus band 3. However, a geometric distance or a Euclidean distance can be calculated in any number of dimensions that we want to. So you can actually do this exact same thing in with 5 or 6 or 7 bands, and essentially you compute a Euclidean distance in 7-dimensional space instead of 2-dimensional space. So we can't visualize that, but it is possible to do that. Okay, and just to quickly bring it back to what are we doing, we've talked about 2 of the methods so far, the algorithms. And so here's an example of how that might play out. We ran a minimum distance classifier on our Yellowstone image, and we can see that water was very well classified. Pink pixels only fall in the lakes, they don't fall anywhere else. Maybe meadow did pretty well, but burned versus unburned here, blue versus kind of light blue, you can see there's a lot of scatter in here, and there's some meadow in here, so clearly there's a number of pixels that haven't been classified successfully. Also, I'll note in a lot of algorithms, you can insert some threshold where if it's not close enough to any of the groups, then just don't classify it. So these black pixels over here essentially weren't close enough to any of our user classes. So it did not issue a classification for those. I believe those are actually shadowed hill slopes. Okay, so let's keep moving with our third algorithm. And this is called Gaussian maximum likelihood. So remember, the problem with minimum distance to the mean was that it wasn't sensitive to the variance in the data. And so this gets around that problem. Essentially, what we can do is we can build a probability distribution for each user class. Okay, so this is a plot of, you can think of it as a histogram perhaps, or if you normalize it, you can think of it as a probability curve. Essentially shows you, here's the possible pixel values in the training group, minus 60 to 40 is their range, and most of them fall kind of here within 30 to 0, but some of them fall out here. And so if you take all this data and you plot it, you can actually build this probability distribution such that if I give you a pixel value like minus 40 right here, this graph allows us to actually say what is the probability of, if you have a pixel that has a value of minus 40, what's the probability that that's actually drawn from this user class? Okay? And so what that allows us to do, of course, is to compare probabilities of being in one user class versus the other. And so let's now visualize that. This is actually the exact same data set we were looking at previously. So it's band 4 versus band 3, but we've now turned the plot on its side, flat, and we've added a third dimension in which probability is the vertical dimension now. And so what you can see is, if you remember sand, the pixel values were quite clustered. They had a low variance. All of the sand pixels in the training group had very similar values. So probabilistically, they cluster and they create a high probability peak, right? With a very small tail. In contrast, urban was very scattered, remember. So urban creates a broad probability field here with a low peak. So if you pick any particular combination of band 3 or 4, the height of this dome here would tell you what the probability of that pixel belonging to urban is. And if it's higher than the probability of belonging to any other class, well then let's call it urban. And here's another view of that exact same figure, except now we're looking down on it and we've converted it into equiprobability contours. Okay, so each of these circles is a probability contour. This one might be like, for urban, might be like a 30%, 20%, 10%, and 0% probability of being part of the class. And so again, we toss in pixel number 1, and it actually would be still classified as corn. But imagine we tossed in pixel value number 2 up here, where previously it was assigned to sand erroneously. Now it would be most likely classified into urban because it has a little higher probability of being in the urban group, even though it's closer to the mean of sand. Okay, so one other thing that this maximum likelihood classifier does for us is it allows us to do something called fuzzy classification. And essentially this is what we've already been talking about. It's this recognition that some pixels may have spectral characteristics that are similar to both classes, to 2 or more classes, right? And it's hard to tell which one they really belong in. And one reason for that, of course, is we know it could be mixed pixel, right? So look at this example. These are big pixels that are subdivided into smaller grids. So this pixel is 100% A. This pixel down here is 100% B. But these two pixels are mixed, okay? And so if you are able to estimate the probability of it falling into A or B, for example, this is about 75% probability of being in A and about 25% probability of being in B, right? If you can use the maximum likelihood approach to come up with these probabilities, then you can decide, okay, well, I just want to classify that into the whichever one's higher. Or if it's 50-50, I don't want to classify it as either. And so if we were doing that, let's say we set a probability threshold for acceptance, like, let's say anything over 20% of B gets classified as B, right? Well, then we would take these rasters. Here's our probabilities of being in B, and here's what our classified map would be. So all these pixels would end up in the user class B. And so fuzzy threshold is nice, fuzzy classification is nice because it allows us to really customize which pixels are going to go into which group, and you can kind of play with those thresholds until you get something you're happy with. So in summary, supervised classification uses training data to divide pixels into user classes. These are functional classes like sand, urban, water, things that you might have on a map. The decision tree classifier is basically a series of sequential binary decisions. And at the end of each decision tree is a leaf, which corresponds to a class. And kind of all pixels get binned into a class. They don't have to, but minimum distance to the mean looks at spectral signatures in 2D or even 5D or 7D space, takes a mean of the training pixels, and then classifies unknown pixels into the closest training group mean. Maximum likelihood essentially looks at the training data in terms of a probability distribution and classifies an unknown pixel into whichever user class it has the highest probability of being in. And then fuzzy classification allows us to really set a likelihood threshold in order to decide where pixels should go. Hope this is helpful. Have a good day.